In section 6.1, we begin our work with vector fields. Now, vector fields can be represented in 2 dimensions or 3 dimensions. If you want to understand what a vector field is, you need to think about things that flow. Anything that flows, such as air, even earth in a landslide, lava, oil spills, the flow of a current in an electrical current or system or through metal, anything that flows, air around a car, can be described with a vector field. Let's imagine, for example, that we want to give a graph that represents the velocity and direction of the water flow on the surface of a river. We can graph in R2 in the XY plane a graph that represents the surface of the river. And at each location on that graph, we can indicate both the direction and the velocity of the flow of the water at that point. The direction is indicated by the direction of the vector we fix at that point, and the magnitude of the vector represents the velocity of the water flow at that particular point. However, since rivers are also 3-dimensional, if we want to give the flow of the river, the whole river and not just the surface, we would need to affix a vector in a 3-dimensional graph space, where at each point it represents the direction of flow and the magnitude of flow of the water. In this way, we can predict by looking at the graph what the flow of that particular object is. Vector fields are often used to represent different kinds of flow. For example, you may see something that indicates some kind of atmospheric change, such as an atmospheric storm like a hurricane or deep sea ocean currents. We can also use vector fields to represent gravitational force or an electromagnetic field. Vector fields have wide applications in all different kinds of fields, where we're indicating something that flows or exerts a force dependent on how close it is to a particular location. We have a few learning objectives for this section. We're going to start by recognizing a vector field in the plane or in 3-dimensional space, learn how one would graph a vector field from a given equation, and identify what we mean by a conservative vector field and its associated potential function. Before we get started, let's take a look at an example of a 2-dimensional vector field. In this case, if you look at the graph, you can see that there are arrows. They're all shaded blue, but they're pointing in different directions at different locations on this 2-dimensional graph. And the vectors are different lengths. This means that when the vector is longer, that the magnitude of flow is faster at that particular point, and it's flowing in the direction that the vector points. So that you can, by tracing your finger along the direction of the vectors, get a sense of the flow of whatever this is describing, whether it's air flowing around a car, lava flowing around a rock on the surface, or some other representation. Let me share my screen and we'll get started. In this image, you can see an example of a 2D vector field and an example of a 3-dimensional vector field. They're both, of course, graphed in 2 dimensions, but they represent different types of vector fields. And the one on the left, it is, of course, a 2-dimensional, which means that we're looking at a particular location in a 2-dimensional surface, and we're predicting the magnitude and direction of some kind of flow at that point. It could be the expansion of heat through a particular material, or the flow of a current through a material. When we're looking at it, if you follow along, the longer the arrow, the faster the flow. And you can follow the direction to see in which direction it is moving. In the 3-dimensional, it's a little difficult to see. It works better on CalcPlot 3D when you can look at it live and sort of rotate it to get a sense of what the flow of the object is. But again, the idea is the same. At various points within a three-dimensional grid, you affix a vector representing something at that point that is flowing, with the magnitude of the vector representing the magnitude of flow, generally velocity, and with the direction indicating the direction in which it is flowing. There are all kinds of vector fields. This is an example of a gravitational vector field. The Earth exerts a gravitational field in a radial pattern, where if you're on a circle centered around the Earth, then at the same distance from the Earth in any direction, you experience the same gravitational force. This is what we mean by a radial field. You'll notice, however, that in this space here between the Earth and the Moon, it's not perfectly radial, because there's a space here where the Moon begins to exert its influence on an object in between the Earth and the Moon. However, if you're looking closer to the Earth, you can see that it is primarily a radial vector field. As long as you're the same distance away from the Earth at any point on that circle, the effect of gravity will be the same. Also notice that the vectors would be perpendicular to that circle at all points. In this case, the gravitational vectors are pointing towards the center of the Earth. The closer to Earth you get, the longer the vector gets, because the greater the gravitational force. There are other kinds of vector fields that you can see. This one represents the flow of water on the surface of a river. The blue indicates the slower flow, and red indicates faster flow. You can tell that over here on the far left towards the bottom that there's an area of faster flow, indicated by the red, as well as the longer vectors. There's also areas near this rock that's in the center of the stream, indicating that there is greater flow close to the rock. If you look at the pattern of the arrows, you can see how the water is flowing on the surface of the river. Notice there's even a place on the backside of the rock where the flow moves completely opposite to the flow around it. If you've ever done any river rafting, you'll know that this exists. You can actually surf a raft on the backside of a boulder in the current, because at one point, the current is completely opposite to what it is in the surrounding water. Now let's go ahead and look at some other types of vector fields. And the one up at the top, you can again see that there are vectors of different lengths pointing in different directions graphed. And you can tell that there are three others that are showing both vectors and colors to represent different values. The one on the lower right is a vector field with contours of the potential function. And when you're looking at these, you can tell that generally speaking, in many graphs, it goes from blue showing less flow to red showing more flow. What we're going to do is talk about what a vector field is and how you produce one. Vector fields really map something in R2 to something else in R2. A vector is a two-dimensional thing if you're going to graph it on a 2D graph, or you can graph from R3 to R3 using a three-dimensional vector. We generally will choose how many vectors we want to use on the graph, because if we use too many, it becomes cluttered and we can no longer see the flow. We often have to scale the vectors on a graph, because if they're too long, they overlap too much. And again, it's hard to see what the flow is. But when we scale them all by the same amount. It's common to scale vectors by a factor of 4, dividing the length by 4 in all cases. Generally, most people will determine a fixed grid, and they will plot what the vector looks like at each point on the grid. and then plot the vector at that point. We're going to think about how we can use these to represent different things in the real world. There is a simpler type of vector field called a slope field or direction field. In a slope field or direction field, we don't use the length of the vector, we simply use the direction of the vector. In a slope field or a direction field, all the vectors have the same length. If they're all length 1, we call it a unit vector field. A slope field indicates the flow of the particular object, whether it's heat, air, water, earth, oil on the surface of the ocean, whatever it is that's flowing. The slope field will show the direction in which the current moves, but it will not show the velocity at the different points, since all the vectors are the same length. These get used quite a bit in differential equations in other classes, and they can be used to show a representation of the solution of a first-order differential equation. We can plot these in CalcPlot 3D by checking the box for used fixed length for all vectors. Let's go ahead and formally define what a vector field is. A vector field in R2 in the XY plane is an assignment of a two-dimensional vector to each point XY of a subset D of R2. The subset D is the domain of the vector field. Likewise, we can define a vector field in R3 as the assignment of a three-dimensional vector in terms of X, Y, and Z to each point X, Y, Z on a subset D of R3. Let's go ahead now and look at some various ways that we can write the vectors down. We studied vectors at the beginning of this semester, and remember we can use either the angle brackets or we can use the standard basis vectors I and J or I, J, and K. If we look at the components in a particular direction, such as the I hat direction, we have P of X and Y in the I hat direction, or Q of X and Y in the J hat direction for a vector in a two-dimensional plane. If we have a vector in a three-dimensional space, we tend to call them P, Q, and R, where P, Q, and R are scalar valued functions, giving us that component of the vector. If these component functions are continuous, then we say that the vector field itself is continuous. Let's talk about how we draw a vector field by hand. One way of doing it is to find, for example, the slope or derivative at a particular point. If we're looking at a particular point on a curve and we compute the slope of the tangent line at that point, that slope has both a direction and a magnitude, and we can represent it in a particular direction. Let's suppose that we want to associate the vector 1, 4 with the point -5, 3. Since the tangent line points in a particular direction and the slope of it, the magnitude of it could be the magnitude, we would simply affix to the point in the two-dimensional grid that has that as the derivative, and we would affix that vector there. Now, this is a relatively long vector for a vector field. So many vector fields will divide this magnitude by 4 to get something that is easier to graph without overlapping with others. It's quite common to plot them at regular intervals moving across in a grid-like pattern. If you want to produce an effective vector field, you want to plot enough vectors to see the general shape, but not so many vectors that it becomes a jumbled mess. Let's take a look at an example, and let me show you what I mean by becoming a jumbled mess. Let's take a look at a vector field here in CalcPlot 3D. In CalcPlot 3D, instead of calling them P, Q, and R, it's calling them M, N, and P. When you're looking at this, it opens up a box which says number of vectors along the x-axis, the y-axis, and the z-axis. If you want to plot a two-dimensional vector field, then you only want one along the z-axis, and you'll want to click the box for restrict view to 2D. Notice also that you can scale the vectors by dividing by a number, and the default here is 4. If I did not divide all the vectors by 4, if instead I let them be their true lengths, let's see what would happen to the graph. Now, when you look at it, it's more difficult to see the flow or the current because they're starting to overlap, and it gets confusing as to which direction they're going. By scaling it by 4, we make it easier to see what the flow of the current is, whatever the object is that's flowing: air, earth, oil, lava, heat, or current. The other thing that can make it more difficult is if you have too many points plotted. Right now, we're plotting 9 along the x-axis from -2 to 2. And if I plotted twice that many, you would see that it gets a little bit more difficult to see, and they begin to overlap. If I do the same along the y-axis, it gets a lot more difficult to see all the aspects of the flow. So when you're doing this, it's a good idea to stick with a reasonable number, something like 9 or 10 across in each direction. And then you can see what it looks like a little bit more clearly. There is sort of an art to it as well as a science. Let's talk about the radial vector field that we talked about earlier when we talked about the gravitational field of Earth. In a radial field, the magnitude of any vector only depends on its distance from the center or the origin of the gravitational field or the radial field. So for example, if I'm out here at this circle, then I know that at that point, the gravitational field is the same at all points on the circle. Notice also that in a radial field, the gravitational vectors are perpendicular to the circle at that point. Let me go ahead and draw in the circle we're referring to so that you can see it. The circle would be the one that goes around at a fixed distance from the source of the gravitational field. And the vectors representing, in this case, the gravitational force, are all perpendicular to that circle. This is different from what a rotational vector field is. In a rotational vector field, the vector at any point is tangent to the circle with a certain radius. And in this sense, it's flowing along the circle in a sense, in a circular pattern. In a standard rotational field, all the vectors either point in a clockwise direction or in a counterclockwise direction. And the magnitude of the vector, again, depends on its distance from the origin, which is similar to a radial field, but it is not necessarily the same in all places. A good example of rotational fields are hurricanes, and you can see this one moving here. This is an example of a rotational vector field. The red represents the higher velocity winds, and then it goes into orange and then yellow, which has lower wind speeds, and then green, and finally blue. When you're looking at these, it goes from high velocity winds out to low velocity winds, moving in a general counterclockwise direction as Katrina slammed into New Orleans right here in 2005. We can also look at other examples, here are two more vector field representations of Katrina hitting the New Orleans coast. When you look at this one, you can see the actual vector fields drawn, but in this case, it's more of a slope field since all of the vectors have the same length. They did indicate the wind speed, however, with color. In this particular one, again, you have sort of the same location or the same situation with color being used to represent the higher wind speed, with the purple being the highest wind speed. And here's an example of Hurricane Sandy when it hit the East Coast in 2012. This was a wider hurricane, so the damage, while very great, was not as great as the damage Katrina did to New Orleans because Katrina landed in a more concentrated area. When you're looking at Sandy, notice that it's extending from almost up to Vermont and New Hampshire, all the way down to South Carolina. Let's now take a look at some 2D online vector field plotters. There are various ones that you can use to plot vector fields. Let's go through a couple of these. We've talked about CalcPlot 3D, and you would plot their representations, whether it's a two-dimensional or three-dimensional, by plotting them in each of these in order. If you want to look at a vector field on GeoGebra, here you would plot what it was in terms of X, what it was in terms of Y, and you can see there's a vector field right here, and you can tell what the flow of it is as it comes out in this direction and then circles around, comes back in. But if you're here, it's flowing directly out. So it depends on where you are as to what the flow is. Wolfram Alpha also has a vector field plotter where you say plot a vector field, and then you say whether you want to, what kind of vector field you want, what the equations are. So this P is equal to Y, Q is equal to negative X. You give your variables and your limits, and by limits, they refer to the actual grid on which you want to plot the vector field from -10 to 10 in both. Here's an example of a vector field given in angle bracket form, -2y, 2x. Remember that we often refer to these as P and Q. If we had 3, we'd refer to them as P, Q, and R. When we're looking at these, you can tell that this one is a type of vector field, and based on the picture, it looks like a rotational vector field where the vectors are moving in a circle. Remember, in a radial, they all come directly towards the source, and the vectors would be perpendicular to a circle about the source. On the other hand, in a rotational field, the vectors lie along the circle or are tangent to the circle at this point. If you want to see what this one looks like, you can plot this one out there on CalcPlot 3D as -2y, 2x. Let me see if I can find where it is. Here it is. So in CalcPlot 3D, instead of calling them P, Q, and R, it calls them M, N, and P. M is the first component in the X position, N is the second component in the J hat direction, and P is the third component in the K hat direction. If you want a two-dimensional vector field, then you will leave the third component as 0 and check the box for restrict view to 2D. If you take that check mark off, it's simply going to show what it looks like, but it's still going to plot it in the plane unless you change and tell how many along the z-axis you want to plot. Right now it says 1, so it's only plotting 1. If I wanted to plot more, I could tell it to plot 5, and then it will give me 5 representations of that particular vector field. And again, it can be a little hard to tell in a 3D vector field what's actually happening. What can help a little bit, if I can get it to go, is to move it a little bit, and then you can see a bit better the flow of the vector field. Let's think about this vector field given in angle brackets by f or equal to 4 times the absolute value of x, comma 1. That means in the p component or the I hat component, our equation is 4 absolute value of x. And in the j hat or q component, it's 1. When we look at this particular one, it's representing the velocity of water on the surface of a river. What is the speed of the water at the point 2, 3? If we want to know the speed of the water at 2, 3, we need to know what the vector is at that particular point. So the vector, and remember these are vectors, so use harpoons if you're writing it by hand, at 2, 3 is going to give us 4 times the absolute value of 2, 1. And this would give us the vector 8, 1. To get the speed, of course, is not including direction. Speed is simply magnitude. So to get the magnitude, we find the magnitude of the vector. The magnitude of the vector represents the speed of the water at that particular point. We find that by squaring each component, adding them together, and then taking the square root. This would give us something like square root of 65 meters per second, which comes out to be about 8.062 meters per second. Okay, so again, the vector indicates the direction that the water is moving at that point on the grid, and the magnitude of the vector indicates the speed. Now, we've already talked a little bit about what a unit vector field is when we talked about slope fields and direction fields. A slope field or direction field includes the direction of flow, but not the magnitude of flow. In a slope field, all the vectors are the same length. If they're all length 1, we call it a unit vector field. There are lots of occasions where you want to know the direction of the flow, but you don't necessarily need to know the velocity of the flow at that point. In that sense, a unit vector field or a slope field may be all you need. Let's take a look at example 3, which asks, is the vector field f of xy equal to negative y comma x a unit vector field? To determine if it's a unit vector field, what we would want to do is find the magnitude of it. In this case, we're going to find the magnitude by squaring each component, adding them together, and then taking the square root. This gives us the square root of x squared plus y squared. That is not equal to 1. And because it's not equal to 1, it is not a unit vector field. Let's go ahead and talk about vector fields in 3D. If we're going to think about a 3-dimensional vector field, we'd like to be able to plot them. GeoGebra has a good 3D vector field plotter, and CalcPlot 3D has one as well. Let's go ahead and sketch and describe the vector field given by g of xyz as the vector 2, z divided by 2, 1. Note that a vector field has variables in its representation, generally speaking, because the length or direction may change depending on the location. In this case, if we look at it, note that the first component is a constant 2, and the third component is a constant 1. That means that it's not changing with respect to x or z at any point. which means that all the vectors in a plane that are parallel to the xz plane are going to have a constant magnitude or length. If we take the y component out of it, then they're all going to be the same. However, if we're looking at the center component, z divided by 2, as z gets larger in magnitude, the vectors get longer. Above the plane, when z equals 0, all the vectors will point up. Below the xy plane, where z equals 0, the vectors will point down. Let's take a look at what example 4 looks like. You can see an image of it right here. And note, of course, that you do have the vectors pointing in different directions. Let's take a look at the vector field in CalcPlot 3D. Okay, that might be a little fast. It's hard to get it going the right speed. There we go. Although I think I've got it going backwards to what it should go. There we go. It's a little bit better now. All right. So you can see the flow as it moves around. Let's go ahead and take a look at the XZ plane when we take Y out of it. If you look at it in the XZ plane, notice that all the vectors in a particular slice are all the same length. That's because the only part of it that depends on a variable is in the Y component. And by looking in the XZ plane, we've taken the Y component out of it. If we looked at a different plane, for example, the YZ, now they're going to change in length because in the Y component, they depend on the value of Z. So as Z gets larger, the vectors get longer. Let's go ahead now and take a look at a vector field that you've been working with, but didn't know that it was a vector field. And this is the gradient. You'll remember that the gradient is a vector which points in the direction of the steepest way to go uphill. When you're thinking of it, the vector is generally given in terms of del of f, where f represents some function. And to find del of f, you take the partial derivatives of that function. That function is called a potential function, and the gradient is called a vector field and the gradient vector field. In fact, it's often called a conservative field because they refer to situations where forces in the physical system has energy conserved. So it's a conservative field because it is conserving energy. Energy is neither created nor lost. There are not a lot of vector fields that become conservative vector fields. It's a relatively high bar to meet. We're going to learn about some conditions that conservative vector fields have, and we'll spend time over the next few weeks talking about how we can know whether or not a vector field is conservative or not, since conservative vector fields have some very nice properties that we like to exploit. And they also describe some physical systems that we study quite often. We call a vector field in R2 or R3 a gradient field if there is a scalar function f such that the gradient of f is equal to the vector field. In other words, the partial derivatives themselves create the vector field. The potential function is the function that you're taking the partial derivatives with respect to. So del of lowercase f equals the vector field uppercase f, when the partial derivatives of lowercase f give us a vector that produces the vector field. If it's a gradient field, it's also called a conservative field. There are occasions in physics where instead of having del of f equal to the vector field, it makes more sense to have negative del of f equal to the vector field. In this class, we'll simply work with del of f equal to the vector field, so you won't have to worry about multiplying by the negative. Let's use technology to plot the following gradient vector field, where we're given the potential function lowercase f of x and y. In order to find the vector field, what we need to do is we need to compute the gradient of f, which is found by taking the partial derivative with respect to x and the partial derivative with respect to y. Go ahead and pause the video to find the partial derivatives, and then turn the video back on and we'll plot this two-dimensional gradient vector field. When you take the partial derivatives, remember that you're going to have to take the partial derivative with respect to x for the first component and the partial derivative with respect to y for the second component. And that gives us the vector field cosine x cosine y for component 1, negative sine x sine y for component 2. This gives us a two-dimensional vector field, and this is what it looks like in GeoGebra 3D, and this is what it looks like in CalcPlot 3D. In CalcPlot 3D, you plot the first component, P, as M, and the second component, Q, as N. Notice the third component is 0 because we are not trying to plot it as a three-dimensional vector field. Notice also that we have only one graphed along the z-axis because, again, it's two-dimensional. We can restrict our view to 2D if we want, or we can simply rotate it so that we see the xy plane. In this case, I have 12 vectors along both the x and the y-axis, but I am again scaling the vectors by a factor of 4. By following the arrows, you can see the flow of something within this particular vector field. We'll study more about flow later in this chapter. Don't forget that you can tell how steep it is by looking at the gradient vectors. The length of the gradient vector equals the maximum partial derivative in a particular direction. It always points the steepest way uphill, and pointing in the complete opposite direction of the gradient is the steepest way downhill. You can investigate the steepness of a graph by looking at the function's gradient vector field. Plotting several level curves can help you to see this. And remember that as the level curves get closer together, the gradient vector's magnitude increases. Let's take a look at what it looks like on the one that we just plotted. On this particular one, if I plot out the contour lines, you can see that as the contour lines get closer together, the vectors, gradient vectors, get longer, right? Now, the other thing that we want to do, and again, you can plot the contour plots by coming over to the contour plotter and clicking on the menu, setting your first level value, step size, and the number of contour plots, and then clicking on Create Plot. And this will give you the contour plots on the particular graph. Let's go ahead now and take a look at example 6. In example 6, we see a function of 3 independent variables, lowercase f of x, y, z, as x squared times the cosine of yz plus y squared z squared. And we're asked, is this a potential function for a vector field? Notice that the vector field is given as a uppercase letter and in bold font because it is a vector field, a field of vectors. And the vector field is given to be 2x cosine of yz minus x squared z times sine of yz plus 2yz squared, and the third component is y squared. When they ask, is this a potential function? What they're asking is, does del of lowercase f equal the gradient vector field? Go ahead and pause the video to compute the partial derivatives of the lowercase function f and determine if they're exactly the same as the components in the vector field. When we find the partial derivatives, we find that the first partial derivative is 2x cosine, oops, did I do? Oh, yes. Looking at the function up here, we get the first partial 2x cosine of yz, which does match the first component of our vector field. The partial derivative with respect to y is negative x squared z sine of yz plus 2yz squared, which again does match the second component of our vector field. So far, it's a match. But the partial derivative with respect to z is negative x squared y sine of yz plus 2y squared z. And the third component of our vector field is simply y squared. Because the third components don't match, this means that the lowercase function f, a scalar valued function of x, y, and z, is not a potential function for the vector field uppercase F. Let's take a look at another example. Let's take a look at the function lowercase f of x and y equal to x cubed y squared plus x. Is this a potential function for the velocity vector field v of x and y given to be 3x squared y squared plus 1, comma, 2x cubed y in angle brackets? Again, in order to determine, we want to take the gradient of function f and see if it matches the vector field. Go ahead and pause the video to work it out, then turn it back on so we can compare our answers. In this case, when we find the first partial derivatives of the function f of x and y, we get 3x squared y squared plus 1 for the partial with respect to x, and 2x cubed y for the partial with respect to y. Each of these components perfectly matches the components of the velocity vector field. The velocity vector field is called a velocity vector field because the vectors represent the velocity of some type of flow at a particular point. When we're looking at this, because the gradient of the function f is the vector field, then we would say that f is a potential function for that velocity vector field. The question you ought to be asking now is, are there other potential functions for the same vector field? And we'll see in just a moment that yes, there are other potential functions, but they can differ from our function f only by a constant. Let's now take a look at a definition that we'll need for one of our theorems coming up. Let's talk about what we mean when we say a domain is connected. When we talk about the domain of a vector field, we say it's connected if you have 2 points within the domain, and you can walk from point 1 to point 2 along some path that keeps you entirely inside the domain. You don't have to leave the domain to get from point 1 to point 2. If you want to think about it, you can say that Colorado is not connected to Hawaii, but Colorado is connected to Alaska. You can drive from Colorado to Alaska without ever leaving the land, but you cannot get from Colorado to Hawaii by walking. Let's go ahead and now consider the uniqueness of the potential functions. In other words, if there's one potential function for a vector field, are there other potential functions that give the same vector field? Let's suppose that we have a conservative vector field. If we have a conservative vector field, then there must be at least one partial function, lowercase f, such that the gradient of f is equal to the vector field. This is what it means to be conservative. Conservative means it is a gradient vector field, which means there must be a potential function. If we have a conservative vector field on an open and connected domain, meaning you can get from point 1 to point 2 without leaving the domain, and you let f and g, lowercase, be two potential functions of the vector field, then there is a constant c such that f is equal to g plus the constant. In other words, they can only vary by a constant because their partial derivatives are identical. If they're both potential functions for the vector field, then their first partial derivatives must be the same. And that means that they can only be different by a constant. We don't have a way yet to accurately predict which vector fields have potential functions and which don't. We know that if it is a gradient vector field, then it's conservative. But if given a general vector field, how do we know if there's a potential function? We'll learn more about this in the coming sections, but for now, we do have one property that can at least tell us when a vector field cannot be a conservative vector field. And this is called the cross-partial property of conservative vector fields. If it is a conservative vector field or a gradient vector field, it does have this property called the cross-partial property. However, there are vector fields that have the property but are not conservative. It's a one-way implication. If it's conservative, it must have this property. But that doesn't mean that because it has the property, it must be conservative. But we can use this to prove a vector field is not conservative by showing it does not have the cross-partial property. Let's take a look at the theorem. Let uppercase letter f be a vector field in 2 dimensions or 3 dimensions, such that the component functions of it have continuous second-order mixed partial derivatives. If they're continuous second-order mixed partial derivatives, by Clairaut's theorem, we know that the mixed partials must be equal to each other. Then it states, if the vector field f of x and y is equal to p as a function of x and y and q as a function of x and y, then we know that the partial of p with respect to y has to equal the partial of q with respect to x. Let's take a look at what happens in a 3-dimensional vector field. If we have a 3-dimensional vector field that is a conservative vector field, meaning that it is the gradient vector field, and there must be a potential function whose partial derivatives give us the vector field, then the cross partial says that the partial of p with respect to the next variable in line, y, has to equal the partial of q with respect to the previous variable, x, and the partial of q with respect to z has to be equal to the partial of r with respect to y, and the partial of r with respect to x has to be equivalent to the partial of p with respect to z. When we're looking at these, it can be a little confusing as to how to think of and how to visualize these in the 3-dimensional case. I will generally draw a sort of a circle like this, and we have this relationship here. The partial of p with respect to the variable that q is the component for, which is y, has to be equal to the partial of Q with respect to the variable that P represents, which is X. So in this sense, they go in both directions. We have the same relationship here between Q and R. If we take the partial of Q with respect to the variable that R represents, which is the Z component, then this has to be equal to the partial of R with respect to the variable that Q represents, which is Y. And finally, our last relationship is going to be the one between P and R. The partial of P with respect to the variable that R represents, which is Z, has to be equal to the partial of R with respect to the variable P represents, which is X. When you only have two, it's not so difficult to figure out. The cross partial means you cross them up. When you have three, it's easier to represent them in a circle and to represent them as double-sided arrows to show the relationship. The proof in the two-dimensional case is assuming that the vector field is conservative, we know there has to be a potential function, lowercase f, such that the gradient of f is equal to the vector field. By the definition of the gradient, that means the partial derivative of lowercase f with respect to x is p, and the partial derivative of lowercase f with respect to y is q. Then if we take the mixed partials, the second partial derivatives, first with respect to x and then with respect to y, we're taking the partial of p with respect to y. And if we take the second mixed partial, first with respect to y, then with respect to x, we're taking the partial of q with respect to x. But because we were told that the mixed partial second derivatives are continuous, by Clairaut's theorem, the mixed partials are equal to each other. So the partial of p with respect to y has to equal the partial of q with respect to x. A similar proof works for the three-dimensional case. And again, being a conservative vector field is a very high bar. Most vector fields are not conservative. You may wonder why we study them so much, and the reason is there are lots of physical systems, such as gravitational fields and charge and a static charge in an electrical field, that we study a lot, and these are conservative vector fields. So we study them because they apply to situations that we often want to model. Let's now go ahead and take a look at example 8. Again, we cannot prove that the vector field is conservative by showing it has the cross-partial property. That's not a proof. There are vector fields with the property that are not conservative. But if it is conservative, it has to have the property. So if we can show the vector field does not have that property, then we know it is not conservative. Let's take a look at our last example, number 8. We are given a vector field G of xyz equal to y, x, xyz, and we're asked, is it possible that this is a conservative vector field? To do this, we need to establish the three cross-partial derivatives. Remember to draw your P, Q, and R in a circular pattern and to connect the pieces like this. Remember that P generally refers to X, Q represents the Y component, and R represents the Z component. Go ahead and pause the video to figure out the cross partials and determine whether or not you think it's possible that this vector field could be conservative. Don't forget that each component of the vector field in order represents P, Q, then R. P is Y, Q is X, and R is X, Y, Z. The three partial derivatives that we have to show are that the partial of p with respect to y is equal to the partial of q with respect to x. When you're looking at your circular graph, remember that p represents the first component with relationship to the x or I hat direction. Q represents the second component in the y or j hat direction, and R represents the third component in the z or k hat direction. The mixed partials can be found by going in both directions. The partial of p with respect to q's variable, which is y, is that equal to the partial of q with respect to p's variable x. The partial of p with respect to y is going to be 1, and the partial of q with respect to x is also 1, so it passes the first test. Then we check the partial of q with respect to z and see if it matches the partial of r with respect to y. In this case, q does not have a z, so the derivative partial is 0. However, the partial of r with respect to y is x times z. It fails this second mixed partial. Because it fails the second cross partial, we know that there is no way it can be a conservative vector field. All conservative vector fields pass all three parts. If it fails one part, it's definitely not conservative. I went ahead and did the third one for completeness, but it's not necessary. In this case, we can also show that the partial of r with respect to x is not equal to the partial of p with respect to z, again reinforcing that there's no way that this vector field can be conservative. There is no scalar valued function, lowercase f, whose gradient gives us this vector field. This is the end of a very short video on vector fields. I hope that you have learned something about what a vector field is and gotten a handle on what it might look like when you plot it in 2 dimensions or 3 dimensions. In our next video, we'll take a look at what are called line integrals. There are 2 types of line integrals: scalar line integrals and vector line integrals. A vector line integral is a line integral done in a vector field. I hope to see you soon for the next video in this series.